in this video, we are going to answer a few questions. The first one is find the DC operating point, which is going to be the ICQ and VCEQ. We're going to find and sketch the DC and the AC load lines. We are also going to find the voltage gain, just the output voltage divided by the input voltage. And last, we are going to find the input impedance and the output impedance. So this configuration is called the common collector because the collector is connected to a DC voltage. Okay, so if the base is connected to a DC voltage, we call it common base, and similarly, when the emitter is connected to a constant source, constant current source, for example, we call it common emitter. Okay, so the first question is to find the DC operating point. So let us find the DC operating point. Okay, so we are going to perform a DC analysis. So DC analysis. So for DC, we are going to remove the AC sources, and the coupling capacitors C1 and C2 are going to be open at DC, right? Because the impedance of a capacitor is 1 over C, right? So if you like J omega C, so when omega equal to 0, that's when we have DC. Then the impedance of the capacitor is 1 over 0, which is infinity. So infinity means open, right? Infinite impedance means open. So the DC network will look like this. So we have R2 just connected to VCC, and we have R1 that's connected to ground, and we have this connected to the base. So we have RE here, and the collector is connected to VCC. Okay, so well, if you like, I could and this is connected to VCC. Okay, so we're told that beta for this network is 100. So R2 is 8 kilo ohms, R1 is 10 kilo ohms, and RE is 1K. All right, so to find to perform the DC analysis, right, we are going to find the Thevenin equivalent connected to the base. So we have this is VCC, we have R2, and then we have R1, and this connect to ground, Now this is the base, right? So the base, the collector, and the emitter. So this is the base. So looking at this base, excuse me. So we can find the terminal resistance in at the base. So RTH, which I'll call RBB. So to find the Thevenin equivalent, because we have a DC voltage source, we are going to replace the DC voltage source by a short. So replace it by a short. Then RBB will be equal to R1 parallel R2. So RBB is R1 times R2 divided by R1 plus R2. So the resistance seen at the base is right, R1 times R2 divided by R1 plus R2. So I'm gonna give the formulas, and then I'm going to give you the numerical values. Now let's find the voltage, the terminal voltage at the base. So gonna redraw the base. So we have this resistor R2, have this resistor R1, okay, and this is the base. So let's say this is ground. We're looking for the voltage here that I will call VBB. Okay, so because we have a series network, we could just do voltage division, which is R1 times VCC over R1 plus R2. So for this, VBB is equal to R1 times VCC over R1 plus R2. So let's calculate those. So we have RBB, which is 8 times 10 divided by 8 plus 10, which is 80 divided by 18, excuse me. So 40 over 9K. Now VBB is 10, just R1, 10 times VCC, which is 10, divided by 10 plus 8. So 100 over 18. That gives me 50 over 9. Okay. Okay, now let's redraw this network. So at the base we have VBB. So let me push it down a little. Have VBB and have RB. B. Connect to the base. So if you like, you put VCC here. Then we have RE here. Now that is our network. Okay. Now this is the collector, this is the emitter, and that is the base. Okay, so to find the base current, we are going to write KVL that includes the base. So let's draw that KVL. So the voltage at the base equal to, so the current here will be IB, current here will be IC, and the current here will be IE. Okay, so the voltage at the base will be equal to RBB times IB plus VBE plus RE IE. So VB B equal to RBB plus RE times beta plus 1 IB plus VBE. Right, because in linear region IC IC equal to beta IB, and IE, which is IC plus IB when we do the KCL. So it's beta plus 1 IB, that's IE. So that's what I substitute in that equation above. So we have VBB minus VBE equal to RBB plus RE times beta plus 1 IB. So IB is given by VBB minus VBE over IBB plus beta plus 1 RE. Okay, so we can just plug in the numbers there, and then we'll find IB and IC and IE. So we are going to notice that IC will be almost equal to IB. Now, so I'm going to plug in the numbers later on as we go on. Okay. Now, so we know IC, right? So we know ICQ will be beta times IB. That's calculated from the equation from what I box above there. And then now let us find VCEQ. Right, so to find VCEQ, right, we are going to write KVL that include the collector and VCE, right? So KVL to find VCE. So if I copy this now down, and paste it down here. So I'm gonna write KVL for that loop. So I have VCC will be equal to VCE plus RE IE. So VCE is equal to VCC minus RE IE. So VCEQ is equal to VCC minus RE IE. Now, so we have the operating point, right? So operating point, which is also called the quiescent point. That is ICQ and VCEQ that we just calculated. So that is number one. So question B. For question B, we're asked to find and sketch the DC load line. So find and sketch the DC load line. So that we're doing this, the DC first, DC load line. So to find the DC load line, I'm still going to paste the network here. Paste it here. Now, so to find the DC load line, we have to write the find IC, right, as a function of VCE. Okay, so to be able to do that, we have to write KVL that include the the collector emitter. So if I did that, I have VCC, which is equal to VCE plus RE IE, where IE is equal to IC. So we have VCC, which is equal to VCE plus RE IC. So when I solve for IC, it's minus 1 over RE VCE plus VCC over RE. So this equation is like mx plus b. So the slope is minus 1 over RC, RE. And B is VCC over RE. So when I plug them in for the DC low line, we know that RE equal to 1 kilo ohm. So IC, which is minus 1 over 1000 VCE plus 10 over 1000. So IC will be 10 to the negative 3 VCE plus 10 to the negative 2. So I can sketch it. Sketch the DC low line. So here is VCE and this is IC. Now, so when VCE equal to 0, IC equal to 10 to the negative 2. So 0.01. And then when IC equal to 0, VCE CE will be equal to VCC 10. Okay, so that is going to be the DC low line, and the Q point, which is VCEQ, and the ICQ are going to be here. Okay, now let's sketch the AC low line. AC load line. So for the AC low line, the DC voltage sources will be grounded because we're doing AC analysis. So those frequencies, so high frequencies, because the capacitor is assumed to be large. So when we do AC analysis, those capacitor becomes a short. So we have the transistor. So we have RE just grounded. The collector is grounded. So we have, so if you like, you can sketch this like this. So RBB is grounded, and we have the AC source with in series with RS VS. Okay, so for the AC analysis, we still need to find the VCE. So small, the lowercase letters mean the AC, right? So we want the current IC as still a function of VCE, right? The AC voltage between the collector and the emitter. So VCE. All right, so 0 will be equal to VCE plus RE IC. Yes, IC almost equal to IE, like we said. So, but we know that when we do superposition, the voltage VCE total will be equal to the DC voltage VCEQ plus the AC voltage VCE. Similarly for the current ICQ, or total, IC total will be equal to the current for when we have the DC only plus the AC voltage IC. So gonna substitute those two into here, so that gives me 0 equal to VCE total minus VCEQ plus, this is RE. Oh, forgot to put the load in, so sorry about that. So the load is here, which is our load. So I'm sorry about that. Right, so here will be RE parallel our load, right, when we do the AC. So IE, so IE parallel our load, and then that is IC total minus ICQ. Okay, so when we solve for IC total, so IC total will give me minus 1 over RE parallel our load, then VCE total plus ICQ now plus VCEQ divided by RE parallel our load. So when I put on the calculator, I have negative. So you know that we know the value of RE from above, right? So the value for RE is 1K and our load is 500. Okay, so we have minus 1 over 1000 parallel 500 VCE total plus ICQ which is 0.0046 plus VCQ, which is 5.3491 divided by 1,000 parallel 500. So it gives me minus 1 over 333.33 VCE total plus 0.0046, plus 5.3491 over 333.3. So the equation for the AC low line gave me negative 0.003 VCE plus 0.0207. So when I sketch the AC low line, so have VCE and IC here, so that gives me this. Okay, so this is 6.88, and the current there is 0.0207. Right, so we'll do the same thing when VCE equal to 0, then IC will be 0.0207, but then when IC equal to 0, VCE will be equal to 0.0207 divided by 0.003. So that is almost, when I put in a calculator, I get, that's where the 6.88 comes from. Okay, and then we had the DC low line, right, which is this. So this was 10, this was 0.01, and that is the key point. So the key point is 5.35, and the current IC was equal to 0.0046, like 4.6 milliamp. So that is the AC and the DC low lines plot together. Now the second question, the third question was to find the voltage gain. See, so let us find the voltage gain. So AV, which is V0 over Vs. Okay, so to find the voltage gain, right, we are going to draw the small signal model. so equivalent circuit. So, and I'm going to do the hybrid pi model. Okay, so the hybrid pi model give me, we have Vs, we have Rs, the DC voltage grounded, right? So have RBB here, then I have R pi here. So the R pi connect to the emitter, and we have this emitter resistance, then we have the load here, and have this dependent source, which is GM V pi, and the V pi is the voltage here across R pi. So, and this grounded. Now, so we have a few things in here. So RO, which is the resistance, right? RO is the resistance connected between the base. Oh no, between the, so this is the base, between the collector and the meter, right? So small RO is connected there. So what is the equation for RO? RO is the early voltage VA, right, over IC. But we're told that VA equal to infinity, right, from the problem statement. So infinity divided by IC, which is infinity. So that means open. So that's why this RO will be neglected here. Now, what is R pi? R pi is connected to the base. So it's VT divided by IB. But what is VT? VT for this BGT is 26 millivolt. Okay, so we can calculate that because we know all the DC analysis. There's IVB, we know IVT, we know IB and all that. So RE, right, that we don't have in here, but I'm gonna give you the equation for that, which is also VT over IE, right, because that's the resistance thing at the meter, right? The resistor that is connected to the meter, that's what I should say. And we have GM. So GM is IC over VT. It's a transconductance. So, well, if I have GM that multiply R pi, so we're going to see this quite a bit. That is what? So GM, which is IC over VT, and R pi, which is VT over IB. So it's essentially IC over IB. Right, so you know that is equal to beta. Okay, so we're gonna keep in mind, so GM R pi equal to beta. Okay, we're going to use this also when we calculate again. Now, so anytime you have this RE, right, and then the pi model, when you look at this network very closely, what you're going to notice is that the voltage at the emitter, which is VE, right? The voltage here, which is a VE. So I'm gonna show you what we call the resistance reflection. Resistance reflection. Okay, so we're gonna reflect to the base, and we're going to reflect to the emitter. So let's reflect to the base. Now, so I get this network. There's a small signal equivalent circuit. Gonna copy that and gonna paste it here, and I'm gonna show you what this reflection that is very useful. Yeah. So when I can draw the network as this, because it kind of makes it easy to compute the gain, right? Otherwise you could just do KV KCL and find it, but this is done quite a bit, so I just wanted to show you how to do that. So we have RB here, BB, and I still have R pi, and the voltage here is V pi. And then, so because the current here is IB, okay, and the current at the meter is beta times IB. So let's just go through the equations. I go to the math. So let's say that I connected a resistor here, R. So I call it R1. So that R1, the voltage, because it's connected, still connected to the emitter, right? The voltage here is still VE, okay? And the dependent current source, which is GM V pi, now I'm gonna connect it to, let's say I call it R2. This is grounded, and the voltage, this still the emitter, right? So the voltage here is still VE. Okay, so to be able to maintain, right, not change the network, right? So the idea is that we have still IB here, okay? And so here we have IC that's going here through the collector. So that's the same current that's going through R2. So for this, VE is R1 IB when I do Ohm's law, which is also equal to RE parallel R load times IE. Okay, but what is IE? IE is beta IB, so R1 IB equal to IE parallel R load times beta plus 1 IB, sorry, so beta plus 1 IB. So that means the resistance seen at the meter, right, when you look from the base, is R1 equal to RE parallel R load times beta plus 1. Okay, and what is R2? I'm going to do the same thing. So we know that VE equal to R2 R2 IC. Okay, so which is also R RE parallel R load that multiplies IE. So that gives me RE parallel R load times times so IC IE is beta plus 1 IB. Okay, so beta plus 1 IB, and this is R2 times beta IB. So that means beta R2 equal to R1 IE parallel R load times beta plus 1. So that means for this one, R2 will be equal to beta plus 1 over beta times RE parallel R load. So it's 1 plus 1 over beta. Okay, RE parallel R load. So there we have it. So anytime we do this reflection, we can just separate the network, and so that means I could just take my network that I sketched over here and copy and paste here, and then I'll replace this by beta plus 1 IE parallel R load, and this will be 1 plus 1 over beta IE parallel R load. Okay, so the output is is found from the emitter, right? So this is a V0. So the voltage gain, so to find the voltage gain, what could we do, right? We know that V0 is beta plus 1 IE parallel R load times IB. Okay, and we know that IB Here, right, there are many ways to do this. We could just calculate the voltage at the base and then do voltage division, right? And here we can find IB, right? So IB will be V pi over R pi, and then we could calculate. So there are many ways to do this, right? So I can find the voltage here at the base, right? If you like, the VB, and I can just then I'll do voltage division, right? So V0, right, which is essentially the same thing. We just need to find IB and then use that to find the V0, right? So I can find VB, then use voltage division. Okay, so to find VB, what do? I can write KCL at this node, right? So VB, so VB minus VS over RS plus VB over RBB plus VB over R pi plus bar plus 1 IE parallel R load equal to 0. So then I will find write this equation, 1 over RS plus 1 over RBB plus 1 over R pi plus beta plus 1 RE parallel R load equal to VS over RS. Okay, so I can find VB from here. So when I calculate that, right, I have VB will be equal to like 1 over RS. Right, you can just put this in a calculator. Right, just nothing really. It looks big, but you can compute this and using a calculator easily. So RE parallel R load times VS. So when I put that in the calculator, I get 0.9752 VS. That's VB. Okay. So then I can do the voltage division, right? So if I take this still and I put it down there so that we have it in front of us. So when I paste it here, okay, so when I paste it here, I know the voltage here is VB, right? So VB, so I can find V0 using voltage division. So V0 will be equal to VB times beta plus 1, right? IE parallel R load divided by R pi plus beta plus 1 IE parallel R load. So we know what VB is equal to, right? So I think I also calculated this, that gives me 0.98, if I'm not mistaken, yeah, 9835 VB. So I have the first equation, just this, right? That's equation number 1. Okay, so you have V0, which is 0.9835 VB. I call that equation 2. So I'll put them side by side. So what do we have? We have V0, which is 0.9835 times 0.9752 Vs. So V0 over Vs equal to 0.95. Okay, so 955 maybe, or 6. Okay, so that's the voltage gain, AV. Okay. Maybe 91, probably. Okay, so that is the voltage gain, which is not too bad. But this is what I want you to notice here. So when we have the common emitter, so common collector, that's what we're doing. So common collector, the gain is so in general, the voltage gain for a common collector is at most equal to 1 and positive. Right? Is at most equal to 1. So almost equal to 1 and positive. Okay, so what is the significance of this? Right, so the voltage follows the voltage at the emitter, right? The input voltage, right? The input voltage right follows the emitter voltage. Right, so that's why this configuration is also called emitter follower. Right, so that is why this configuration okay is also called emitter follower. Okay, so this emitter follower is mostly used when you design a multi-stage amplifier, and this emitter follower will be at the output. So we are going to do some multi-stage amplifier design in the subsequent videos, and I I'm gonna elaborate more on why, right, this is, so useful, right? Because let's say you wanted to drive, you're doing an audio um, amplifier, and the output stage, right? Because the microphone, the speaker, or not the microphone, the speaker, the resistance is small. So when you have small resistance for the speaker, right? Um, because the input output impedances, so that we're going to talk about those in a minute, right? So you're going to see why this is mostly used as uh, for an output stage. But what I want you to take away here is that the gain, right, is the sign is positive, right? The voltage gain AV is positive, right? Is positive. So the amplifier does not introduce any phase shift. Okay, right? And the input voltage follows the output voltage at the emitter. Okay, so now let's answer. But please stay tuned. We are going to do some real amplifier design later on in subsequent videos, right? Because it's nice to solve this, but the applications is even more important. Okay, so now let's find, so D, right? Let us find the input and output impedances. So let us find the input and the output impedances. Okay, so I'm gonna do the input impedance first, and then next I'm going to do the output impedance. Okay, so let's do the input impedance. Okay, so the input impedance is found looking at the base from what we're given. So I'm gonna sketch my network. Well, if you like, I still have it. Okay, just paste it. No. So okay, just it's not that. So let me just sketch it. So we have RS, PS is here. We have RB, RBB, and we have RPi, and we have RE, parallel our load here, times beta plus 1. So the current here is IB. Now, so the input impedance is looked at right from here, because that's where we connect the source, the input source. Okay, so when we look at that, what do you see? Right, so you see that when you look at that point, which is the base, then RB, so Rin will be RBB, will be in parallel with RB plus beta plus 1 times IE parallel load. Okay, so I calculated that, and that gives me 3.9334 34 times 10 to the 3 ohms. I mean 3.934 kilo. Okay, so please keep in mind that this impedance is high, so high input impedance. Okay, now let's calculate the output impedance. Okay, so to calculate the output impedance, well, I should have the other piece, the other side of the network drawn as well, right, to make it complete, right, which is E parallel load times beta plus 1, and 1 over 1 plus beta, 1 over 1 plus beta, or beta plus 1 over beta. Okay, so it's beta plus 1 divided by beta. Okay, so this grounded, and this is also grounded, and this is GM V pi. Okay, now for the input impedance, maybe I should mention that also from here. So maybe let's do that, right? So to find the input impedance before we do the output impedance, there's another way to do it. Is if I copy this network, let me show you this as well. Maybe you probably prefer that one. Okay, so to find the input impedance, right, looking at the base, so what do? Okay, just place a source here. Okay, and I'll put a test source here, so which is Vx, and the current supplied by the test source is Ix, so Rin will be Vx over Ix. So if you agree with me, we could just have the equivalent resistance seen by the source will be RBB parallel pi plus beta plus 1 RE parallel load, right? So as you can see, in, which is Vx over Ix, is RBB parallel pi plus beta plus 1 E parallel load. Okay, so now let's find the output impedance. Output impedance. So for the output impedance, I am going to still paste the network here. Alright, so let me draw it. That's fine. So we have so we have RS, and then we have RBB, and we have RPi, we have R, also beta plus 1, that multiplies RE parallel R load, all right. So well, to find the output impedance, we could do it using the test source method as well. Okay, so to use the test source, what do we do? I'll place a test source at the emitter. Okay, so let me use that method to show you how you can also do that. So we have RE, okay, and remember that we do not account for the load, right? When you find the input impedance, the output impedance, right? We don't account for the load, so we can so the output impedance is looking this way, okay, with the load not included. So that's out, right? So if you like, I have the network here still there without the so this is a GM VPi. So that the location where I'm trying to find the output impedance, I could place a test source there, Vx or Vt, and the current here is Ix. So R out will be Vx over Ix. All right, so to find the output, right? So what I'm going to do, okay, just so what do we do? When you place a test source, you replace this by a short, right? So remember that when you place a test source at the output, then you replace the input voltage Vs by a short. Okay, and here we have a very simple network that we can solve for that current Ix. So I still have Vpi, right, which is there. So I will write KCL at our node, okay, and find the current IX. So if you like, we have, I'm gonna simplify the network down to, so we have RX parallel RB parallel so RBB, so I can combine them, and then those are in series with our pi. Okay, so if I combine this side of the network, you see that they are in parallel, and I have them in series with with our pi. So that means the network becomes so I have this, which is RS parallel RBB plus R pi. Now in parallel with RE, and then I have Vx here. The current supply is Ix, and then we have this current source, which is GM V pi. Okay, so I have Vx here, so I could write all this current, this, so sum of the current coming to the node equal to sum of the current leaving the node. So we have Vx over this, I call this so RS1. Okay, let me just call it RS1. So RS1 plus 1 over RE equal to Ix plus GM V pi okay. So what is V pi? So here we have Vx right there. So V pi equal to negative Vx times R pi divided by R pi plus RBB parallel RS, right? Doing voltage division. So I combine this right into one, and I do voltage division, right? So we have this, which is RS parallel RBB. Then I have R pi here, and the voltage here, but I have Vx right there. So the R pi and RS parallel RB are in series. I could do voltage division, so that's where this comes from. Okay, all right, so then I know this is also Ix minus GM R pi, and then we know that was equal to beta. right? So Vx over R pi plus RBB parallel Rs. Okay, so this is a little complicated because of the presence of Rs. If the input voltage did not have the input resistance Rs, all this would be a lot simpler. Okay, so we have Vx over Rs1, which is Rs parallel RBB plus R pi, now plus 1 over Re plus, okay, so GM R pi is better, so better Vx over R pi plus RB B parallel Rs. Alright, this like kind of looks big, like complicated the equations, but once you can just calculate those values and plug them in, as you can see, it's quite, easy. Right, it's not, I'm not saying easy, but it's not that, yeah, it looks scary, it looks like complicated, but when you calculate those values, you know how to calculate parallel resistance, equivalent resistance. So you plug them in, and this is just a very simple equation that you can solve. Okay, so we could solve, we could solve for, so Vx, which is 1 over Rs parallel RBB plus R pi plus 1 over Re plus beta over R pi plus Rs parallel RBB equal to Ix. So this is not that bad. So we have Vx, which is beta plus 1, divided by Rs parallel RBB plus R pi plus 1 over Re equal to Ix. So as you can see, R out, which is Vx over Ix, is equal to beta plus 1 . Well, let's write this also to simplify that a little bit. So we have beta plus 1 Re plus Rs parallel RBB plus R pi divided by Re times R pi plus Rs parallel RBB, which is Ix. Right, so R0, which is Vx over Ix, is Re times R pi plus Rs parallel RB B divided by beta plus 1 Re plus Rs parallel RBB plus R pi. So when you calculate that, you are going to get 6.52 ohms. Okay, so the output impedance is low, right? Which is so small output impedance, small output resistance. Okay, so for the common collector or emitter follower, for the emitter follower, which is also called common collector. Okay, we have high input impedance, high input resistance, input resistance, and small output resistance. That is why it's called sometimes called impedance transformer, resistance transformer. Thank you.